I wanted to tell a simple story, maybe not perfectly accurate, of how J.J. Thomson may have gone through his work with the cathode ray tube. So over here on the left I have two batteries that we're going to use to create movement of electrons through a vacuum. This tube here looks like a hot dog. Is our tube of glass. It has very little air molecules in it. It's a vacuum. And this is a metal surface that has a negative charge, and this disc with a little hole in it has a positive charge with a high potential. And this metal lets electrons go from the surface. And this arrow is going to represent our electron having a certain velocity. Well, as it comes in through that disc, flies through, doesn't get picked up by the plate, having a lot of velocity, we're going to apply a potential, smaller one, across these plates here, above and below, and that'll bend the path. So without the charge, that electron comes straight across. But with that charge applied through these plates, the path of the electron bends. It actually has more of a parabolic drop as it comes down, and then we hit the wall of this glass tube. And if there's something that fluoresces, we can see where it hits here, and we can see where it hits here, a distance. We'll call that drop y. And we'll try to just think of maybe not what equals, but what would it be dependent upon, that amount of drop? Well, certainly the charge of the plate here above and below would cause that drop, but it has to interact with the charge of our electron, so we'll call that little e, the charge of our electron. And we would also realize that if the mass was really high, then that would reduce the drop, because it'd be a lot more work to push that large mass down or to pull it down with the charge. We'd also know it would be somewhat dependent upon the velocity. If that's a very fast electron coming across, it may not drop that much. Well, it turns out we're not too far off if we kind of just think of those in general as variables that control the drop. The drop actually can be equated, not just proportional or so, or qualitative related. It's equal to 1/2 acceleration due to this field applied times t squared. We had to square because this force continues as this thing comes across to apply, and the arrow, the amount of movement down increases as you actually move across here. It accelerates that motion down. And if we pull these two together, it turns out that the amount of drop is equal to 1/2. If we start plugging in some variables that J.J. Thomson could have either measured or found values for, so that's 1/2 Q. He could determine the charge of the plate. I'll put a check mark to that. E, he didn't know. He was looking for that. X, the distance across here, because it turns out we can replace that t, because velocity equals distance over time. You can switch out the v and the t, switch those, and we can get E times x over v squared, and we still get the mass showing up on the bottom. Well, x he could measure, that distance from here to here. Velocity, through some really cool work, could be measured. And so if you take all of that and shove it to the side and move it to the other side, the only things that were unknown was the charge to mass ratio. J.J. Thomson was able, through some equation maybe like this, maybe not be exactly what he did, but very much close to what he had as his equation, could find out the charge to mass ratio. That's pretty neat.